You pull out your phone, you tap a button that says our request ride or order food, and you just wait.
Yeah, it feels like magic.
Right. To you, it looks like this seamless, almost invisible process. You watch a little car icon crawl across the map, and you really think nothing of it. But underneath that single tap is an industrial-scale digital assembly line, just moving at the speed of light. And today, we're tearing that assembly line apart.
We really are.
We're looking at a fascinating paper from SIGMOD 2021. It's titled Real-Time Data Infrastructure at Uber by Yupeng Fu and Xinmei Somen. And our mission for this deep dive is to decode how an organization actually processes like petabytes of data and trillions of messages a day in real time, just making these incredibly complex decisions in literally seconds. So, okay, let's unpack this.
Yeah, and to really appreciate the engineering feats we're going to explore today, we first have to set the baseline scale of the problem because it's huge. As of October 2020, which is a snapshot this paper gives us, Uber's data centers were generating trillions of messages every single day.
Trillions, with a T. That is it's a staggering flow of information.
Exactly. And the engineers faced three competing scaling challenges here. First, just scaling the sheer volume of data itself as the company grew exponentially. Second, scaling the use cases.
Right, because different teams need different things.
Exactly. You have dynamic pricing algorithms that need to run in like milliseconds, competing for the exact same resources with business dashboards that need absolute mathematical precision.
Yeah, a dynamic pricing algorithm doesn't care about the exact same metrics as the finance team's end-of-month dashboard. One needs absolute speed, and the other needs perfection.
Right. And the third challenge was scaling the users. The people actually building pipelines on this infrastructure, well, they range from hardcore systems engineers to operations personnel who literally had no coding background whatsoever.
Wow.
Yeah, so Uber needed to build this unified platform that could serve all of them simultaneously without the entire system just, collapsing under its own weight.
And because they had to move incredibly fast to survive this, unprecedented scale, they leaned into the power of the crowd. They took existing open source technologies, but then they heavily customized them to survive their specific environment. So we are going to start at the absolute foundation, just getting the data from point A to point B.
Right, the highway. The backbone of this data highway is Apache Kafka.
Yeah.
In the data engineering world, Kafka is a very mature open source system for handling streams of events.
Right. So every single action, like a driver turning a corner or a restaurant accepting an order or even a rider just opening the app, that becomes a message published to this Kafka highway.
Exactly. But the thing is, out of the box, Kafka simply wasn't designed for trillions of daily messages in a single cluster. It just couldn't handle it. So they had to build this custom layer called cluster federation.
Because if standard applications have hard-coded directions to specific physical clusters of servers, that system breaks down the second a server fills up, right?
Absolutely.
Or if a cluster needs to go offline for maintenance. Moving data around would require a coordinated manual update of thousands of client applications. So they must have needed a layer that abstracts that physical reality away, like a traffic cop.
Yeah, that is the perfect way to visualize it.
Right.
The federation layer creates logical clusters. The applications, they don't need to know the physical address of the server anymore.
They just ask for directions.
Right. They just tell the federation layer, hey, send this to the trip events topic. The federation layer hides all that physical complexity and quietly routes the data to whatever physical server has the capacity at that exact moment. It totally decouples the software from the hardware.
That's brilliant. And while we are talking about routing traffic, we have to look at how they handle crashes on that highway, because they built a customization for Kafka called a dead letter queue.
This is such a smart feature.
It really is. Imagine a massive post office mailroom, right, with a conveyor belt moving millions of letters. Suddenly, a letter comes down the belt with a completely unreadable smeared address. In a standard data system, the scanner stops. It tries to read the address again and again and again.
And it just blocks everything.
Exactly. The entire conveyor belt halts. All the perfectly good mail backs up behind it just because of this one corrupted envelope. A single bad trip receipt could literally pause a massive chunk of Uber's data processing.
Right, and what's fascinating here is how the dead letter queue entirely eliminates that catastrophic bottleneck. Instead of stopping the belt to decipher the bad data, the system just grabs the unreadable letter and tosses it into a specific bin, the dead letter queue.
Oh, I love that. So it just gets it out of the way.
Exactly. The conveyor belt keeps moving at full speed for the rest of the mail, and then later an engineer or an automated script can go to that specific bin, figure out what went wrong with that one message, and reprocess it. Live traffic is never, ever interrupted.
So keeping the data flowing leads to another massive architectural shift they made. They built the consumer proxy. Because historically, Kafka relies on a pull model, right?
Yes, exactly.
Tens of thousands of different applications constantly pull Kafka, constantly asking, like, do you have new data for me? How about now? How about now?
Yeah, and that polling approach creates two massive problems. First, it puts an artificial cap on parallel processing. Kafka divides data into partitions, and in a pull model, a partition can typically only be read by one consumer in a group at a time.
Okay, that makes sense.
And second, Uber had maintained client library code in thousands of different applications across multiple programming languages. If they needed to upgrade a Kafka feature, coordinating the update of all those clients took months. It was a nightmare.
Wow, okay, so if polling Kafka constantly is artificially capping their processing power and making upgrades a total nightmare, they must have reversed the relationship. Did they put a layer in front of Kafka to, like, push the data out instead?
They completely flipped the model. The proxy layer actively pulls the data from Kafka and dispatches or pushes the messages out to the services via standardized network calls.
So the apps just chill and wait for it.
Right. The applications just wait to receive it. This single change decoupled the consumption of data from Kafka's internal partition limits, and that unlocked massive parallel processing for slower consumer applications. Operationally, the platform team now only had to manage and upgrade their central proxy, rather than thousands of scattered client apps.
Man, that is elegant. Okay, so the highway's built, the data is flowing flawlessly, the corrupted messages are sidelined, and the data is pushed out efficiently. But raw data on a highway is just noise until you actually run the numbers. We need a brain to do the math.
Yes, and this is where we transition to stream processing. The technology they chose to act as the brain is Apache Flink. They tested Flink against some major competitors in the space, specifically Apache Storm and Spark.
But they ultimately went with Flink for some very specific reasons, right? Primarily memory efficiency and recovery speed.
Yeah, recovery speed was the absolute defining factor. If a massive backlog of data built up, say, millions of messages queued up after a temporary network hiccup storm, would take hours to process the backlog and catch up to real time.
Hours. That's brutal.
Right. But Flink could recover and clear that same massive backlog in just 20 minutes. When a business operates entirely in real time, an hours-long delay in pricing or matching is catastrophic. 20 minutes to chew through millions of backlogged events while simultaneously processing new, live ones is just a remarkable engineering feat.
And the paper highlights a tool they built on top of this called Flink SQL. They basically wrapped this highly complex distributed stream processing engine in a basic SQL interface. The goal was to democratize the code, right?
Yeah, exactly.
They wanted non-technical users like city operations managers or business analysts to build their own real-time data pipelines simply by writing a standard SQL query.
It sounds incredibly empowering on paper, doesn't it? You give the broader company access to the real-time processing engine without requiring a degree in distributed systems.
Well, wait, let me make sure I'm wrapping my head around this. If you hide all that complex stream processing logic behind simple SQL for non-engineers, doesn't that create a massive operational nightmare for the platform team who actually has to keep the servers running?
I think so, yeah.
I mean, a non-technical operations manager could write a terribly inefficient query that accidentally demands 100 servers to execute. If the user has no idea how the engine works under the hood, who keeps the servers from melting down?
You zeroed in on the exact danger of this approach, and the paper openly admits it. Giving non-engineers the power to spin up Slink jobs adds an incredible amount of operational overhead. To survive giving everyone access to a Ferrari, Uber's platform team essentially had to secretly build an automated driving system to stop them from crashing. They built a highly sophisticated, unified job management layer.
Okay, so how does that management layer actually police the jobs? Like, what is it looking for?
Through empirical analysis and just intense automation. The job manager constantly profiles the jobs. In stream processing, you have different types of workloads.
Like what?
Well, a stateless job like simply filtering out all the rides in London from a global stream doesn't need to remember anything, but it needs heavy CPU power to process the volume.
Okay, got it.
But a stateful join job, say, continuously matching a massive stream of rider locations with a separate stream of driver locations needs massive amounts of memory to hold the state of both streams simultaneously. The management system watches these jobs run, learns their profiles, and auto-scales the required CPU and memory on the fly without human intervention. Furthermore, if a job gets stuck, this layer detects it and automatically restarts it.
Okay, so the brain is processing the data perfectly. It is filtering the events and joining the streams. But Flink isn't a search engine. A processed answer isn't useful until a human or an algorithm can actually ask for it and see it instantly.
Right, you need a way to serve it up.
Exactly. If an Uber Eats restaurant owner wants to suddenly look at a dashboard of their sales, they can't ask Flink. They need a memory bank that can serve up those processed answers the moment they are requested.
And for this, they utilize an online analytical processing, or OLAP, system called Apache Pinot. OLAP systems are specifically designed for answering multidimensional analytical queries swiftly.
As opposed to transactional databases.
Right. Unlike transactional databases that are great at updating a single row, OLAP systems organize data in columns. This makes them lightning fast for aggregations like, show me the sum of all sales in this city over the last hour. They evaluated Pinot against competitors like Elasticsearch, and Pinot used 4 times less memory, 8 times less disk space, and was 2 to 4 times faster at executing complex queries.
Wow, speed is the absolute currency here. But I think the most crucial customization they added to Pinot was upstart support, because this solves a massive real-world physics problem for a distributed database.
It really is a huge deal.
Right. Because think about it, a ride happens, the data is processed and stored. But then a rider complains the route was wrong and the fare needs to be corrected. Or a delivery status updates from arriving to delayed. The system has to modify a specific record that has already been permanently stored.
And updating a single record across a massive, globally distributed database scattered across thousands of servers is notoriously difficult. If you don't design it perfectly, the whole database grinds to a halt.
Because usually servers in a distributed database act like coworkers trying to edit the exact same paragraph in a shared Google Doc at the same time. They have to constantly stop, lock the document, check what the other person is doing, make the change, and then unlock it. It creates massive friction.
That's a great analogy.
Thanks. So Uber engineered a shared nothing upstart architecture for Pinot, right?
They did. They engineered mathematical routing so that all updates for a specific primary key, like a specific trip ID, are always routed to the exact same physical node.
So the server holding the data never has to check with any other server. It mathematically knows it is the only one authorized to update that specific record. It just acts alone, completely friction-free.
Exactly. Pinot handles these updates flawlessly, but it lacked full SQL support. It couldn't execute highly complex table joins on its own. So to solve this, Uber combined it with Presto. Presto is fantastic at executing complex SQL queries, but it is historically a slower batch processor.
Ah, okay. So think of Pinot as the lightning-fast librarian who knows exactly which shelf every single book is on and can retrieve them in milliseconds. And Presto is the brilliant researcher who can read all those books and synthesize a highly complex thesis. You need both to get a fast, smart answer.
That's a spot-on way to put it. Presto acts as the query engine, but it pushes the heavy lifting like the searching and filtering down to Pinot's super-fast indexing. Together, they execute massive, complex queries with sub-second latencies.
Okay, so we have the highway, the brain, and the memory bank. Let's look at how this machinery actually drives the app in your hand, starting with surge pricing.
Right. Dynamic pricing is perhaps their most demanding use case. It uses Flink and Kafka to calculate the exact ratio of rider demand to driver supply for very specific geographic areas. You know, those little hexagons you sometimes see on the app's map.
And this is where we run into the reality of physics and the CAP theorem. The CAP theorem basically states that in any distributed data system, you cannot have both perfect consistency and perfect availability when the network connection gets messy. You just have to choose one.
Yep, you can't have it all.
For surge pricing, Uber chose freshness and availability over perfect consistency.
And if we connect this to the bigger picture, why is choosing freshness the correct engineering decision for pricing? I mean, why not wait for perfection?
Well, think about traffic navigation. It is like choosing between getting a slightly imperfect map right this second so you can immediately avoid a massive traffic jam versus waiting 10 minutes for a mathematically flawless map.
When it's too late.
Exactly. When the traffic jam is already over and you are currently stuck in the middle of it. For surge, if a few data points from a driver's phone arrive late due to a bad cell connection, the system simply drops them. It does not wait. It must output the new price for that geographic hexagon every few seconds, no matter what.
Right. But Not every use case sacrifices consistency, though. The Uber Eats restaurant manager dashboard, for instance, requires complete financial accuracy. Restaurant owners need to see their exact sales and service quality.
Yeah, you can't be dropping data when it comes to people's money. For this dashboard, they need speed, but they also need mathematical perfection. So they use pre-aggregations in Pinot. They essentially sacrifice query flexibility.
How so?
Well, the restaurant owner can't ask the dashboard just any random, obscure question. But in exchange, the dashboard loads instantly because the answers to the limited questions they are allowed to ask have already been pre-calculated and stored.
Yeah, that makes sense. But sometimes you do need to ask incredibly obscure random questions, and you need the answer immediately. This leads to one of the most powerful real-world applications in the paper, which was the EatsOps automation during the COVID-19 pandemic.
Oh, this part was wild. During the height of COVID in Europe, regulations were changing daily. A city government might suddenly mandate that restaurants could only have a maximum of, say, 5 couriers waiting outside at any given time.
And they needed a way to enforce that instantly.
Right. The operations team didn't have months to write new software to enforce this. They used this exact ad hoc querying system, Presto, running on top of Pinot, to instantly monitor courier capacity at specific restaurants in real time. Once the dashboard showed the metrics, they injected rules into the automation framework to actively limit the orders flowing to that specific restaurant, just to keep everyone safe and legally compliant.
It's incredible. But this raises an important question. All of this architecture is remarkable when the servers are running. But what happens when an entire data center gets wiped out? A power grid fails, a backhoe severs a main fiber optic cable, or a natural disaster strikes.
Yeah, an error screen saying the server is down is not an option when you are actively managing the transportation grid of a major city. We have to talk about disaster survival.
And this is where their multi-region strategy comes into play. For highly critical systems like surge pricing, they use an active-active strategy. They literally run the exact same massive Flink processing pipelines simultaneously in entirely different geographical regions.
Wow.
Yeah, an overarching service acts as a referee, coordinating which region is currently the primary. If a data center in region A suddenly goes completely dark, region B is already actively computing the exact same data in real time. It seamlessly takes over as the primary. You, the user, never even notice it happened.
Wait, running the exact same heavy computations simultaneously on different sides of the country? Isn't that incredibly expensive from a server cost perspective?
Oh, it is exceptionally expensive.
Yeah.
But the business cost of a total global outage for even 5 minutes far outweighs the server costs of redundancy. However, for financial data, the actual dollars being processed, you cannot use an active setup, and you certainly cannot drop late messages like you do with surge pricing.
Because you can't double charge someone.
Exactly. You cannot lose a single penny, and you cannot double charge a user because 2 regions process the same receipt.
So for financial data, they use an active-passive setup, right? Only one region processes the data, but it continuously synchronizes its exact position in the data stream. It's offset with a backup region.
Yes. Think of the offset like a physical bookmark in a very long novel. The primary region is reading the book and moving the bookmark. If the primary region's data center loses power, the passive backup region wakes up, opens the book, finds the exact location of that synchronized bookmark, and resumes reading exactly where the other left off. This ensures absolute consistency with zero data loss.
Now, here's where it gets really interesting. We've talked about surviving natural disasters in real time, but what if you need to survive a human mistake from the past?
Oh, the dreaded historical fix.
Right. What if a developer realizes there was a logic bug in the code for the last 3 months, or a data scientist wants to train a new machine learning model to see how the system would have behaved if a new feature had been active last year? They need to rerun historical data.
And in data engineering, this is known as the backfilling problem. Traditionally, it has been an absolute nightmare.
Oh yeah, the old industry standard was the Lambda architecture. You literally had to maintain 2 completely separate systems, one streaming system for real-time data and one batch processing system for massive archives of historical data. Developers had to write the same logic twice in different languages and fix bugs in 2 different places. It was miserable.
It really was.
And then came the Kappa architecture, which tried to use the real-time streaming system for everything, but that meant you had to keep months or years of historical data sitting in the fast, expensive Kafka highway, which is financially ruinous.
Exactly. So
Yeah.
Uber engineered an elegant evolution they call Kappa plus Ka.
Right, because if keeping data in Kafka is too expensive, but writing code twice for Lambda is a nightmare, they must have found a way to point the real-time stream processing code directly at the cheap historical storage archives.
That is exactly the mechanism of Kappa plus Chi. They modified Flink so that a developer can take their real-time streaming code, make zero changes to it, and point it directly at the massive historical batch data stored deep in their Hadoop Hive archives.
So, to the code itself, it feels like it is processing a live stream of events, but it is actually time traveling through petabytes of frozen historical data?
Yeah, they just throttle the Flink job so it doesn't choke on the massive volume of the past. Developers can process months of history using the exact same logic that runs the live app, completely unifying the environment. You test your ideas on the past, you seamlessly transition them to the present, and it all runs on the exact same infrastructure.
That is wild.
What is truly remarkable is that they achieved this without having to migrate to entirely new paradigms. They deeply customized what was already there to bend the technology to their specific will.
So what does this all mean for us? We've journeyed from the open source federation of the Kafka highway into the auto-scaling brain of Flink to the high-speed shared nothing memory banks of Pinot and Presto. We've looked at surviving data center deaths and time traveling through historical archives. And, well, all of this incredible invisible machinery exists just to make sure a car or a meal shows up when you press a button on a piece of glass.
This deep dive proves something fundamental about the modern digital economy, I think. In a world of absolute information overload, the most valuable infrastructure a company can possess isn't just the capacity to store data. Anyone can buy server racks and hard drives.
Right.
The true competitive advantage is the architecture that makes that massive ocean of data actionable within seconds.
Actionable in seconds. And that leaves us with a final thought to ponder. As technologies like Kappa Plus continue to evolve, completely unifying how we handle live events and historical processing, and as modern tiered storage solutions begin to entirely separate where data physically lives from the engines that compute it, are we approaching a near future where the line between real-time events and historical archives completely disappears?
It's a huge question.
What happens to businesses, and more importantly, what happens to artificial intelligence when every single piece of data a company has ever generated since its inception can be queried, analyzed, and acted upon just as instantly as an event that happened 1 millisecond ago? Just think about that the next time you pull out your phone, tap that button, and watch that little car start to move.
It changes the boundaries of what is possible.
It really does. Thanks for joining us on this deep dive.